Guest is Gerald Commission, CEO of Amarantus.
Thank you very much. I'm Gerald Commission, President and CEO of Amarantus. My background is a Stanford University engineer, former football player in the Canadian Football League, and then joined my father, who will be speaking here shortly, Dr. John Commission, who's the former head of the Neurotrophic Factors Group at the NIH, as well as the Neurotransplantation Lab, and co-discoverer of MAMF, who will be presenting data on our rodent neurorestoration model of Parkinson's disease for our lead program, MAMF. Following Dr. John will be Dr. Joe Rubenfeld. Dr. Joe is the founder of Amgen.
That's what I'm talking about.
He has a significant history in the biotechnology space, having been there in its early beginnings, been involved in the development of a number of drugs, including the inventor of amoxicillin, and one of the early guys who was responsible for EPO's development. So, a little bit about Amarantus. We're a publicly traded biotech company trading on the over-the-counter bulletin board. Our stock symbol is AMBS. We are based in Sunnyvale, California, and our programs are focused on Parkinson's disease, both therapeutics and diagnostics. Safe harbor statement, please read. So, from a highlight standpoint, we work in Parkinson's disease. Parkinson's disease is a $3 billion market, growing at roughly 8.6% annually, according to Data Monitor. There are roughly 6 million patients worldwide, and the incidence is expected to double by 2032. It's characterized, most importantly, by the fact that there are no marketed drugs that slow, stop, or reverse the progression of Parkinson's disease, the underlying cell death of dopaminergic neurons, or reinnervate the striatum. We are focused on the development of MAMF, which stands for mesencephalic astrocyte-derived neurotrophic factor. Trophic factors are a promising category of drugs for Parkinson's disease because they rescue cells from death and have the ability to reinnervate areas of the brain when delivered appropriately. We're working on MAMF as a potentially disease-modifying drug for Parkinson's as a potential curative therapy in so far as what that means. There are also potential other apoptosis-related applications of MAMF. John will be speaking about the Parkinson's application and most specifically the data we have just completed, and Dr. Rubenfeld will give an overview of the potential of MAMF as it relates to other applications. Beyond MAMF, we own a portfolio of assets in the diagnostic space related to Parkinson's disease, Alzheimer's disease, ALS, chronic myeloid leukemia, breast cancer, as well as several other diagnostic assets, and an Alzheimer's diagnostic asset which is based upon immunology. Both sets of diagnostic assets are ready to move into second-stage clinical studies. So, without further ado, Dr. John, please present the data.
Hi, good afternoon. So, there are certain movements, like walking and shaking somebody's hand and eating, and something called slow movements. And those movements are controlled by these structures here, collectively known as basal ganglia. And the brain tells these structures what to do via the striatum. And the striatum is in turn innervated by that structure called the substantia nigra. And this is a very important innovation, because when that innovation goes away, when the dopaminergic neurons die, then the circuit becomes dysfunctional. And this is when you see the signs of Parkinson's disease. So people, when they want to walk, they get rooted to the ground. When you want to shake somebody's hand, your hand gets frozen in midair and so on. So the whole point of this talk, as Gerald intimated, and the whole point of our program is to try to restore function to this system. So where we are at the moment, for the past 50 years, we've been concentrating on trying to restore function to the striatum. This is really equivalent to having a plant that is dying because it doesn't have water, and you try to fix the plant by spraying water onto the leaves. What you really want to do is to water it and give it nutrients from the root, that's the cell body. And this is what we are trying to do. So there is the inevitable comparison. The drug standard in this field was GDNF. As you can see from this, that MAMF appears to be superior to GDNF in many important modalities. So how do you go about doing this? First of all, you get very competent collaborators, because this is a difficult business. So we've had 4 collaborators doing 4 different projects, and so the results I will show you are from those collaborators. So I want you to understand how we go about doing this. You start here, you give a drug or a toxin that kills the dopaminergic neurons, and you try to simulate Parkinson's disease, because that is what happens in Parkinson's disease. So if you look here, this is an age-matched control in which person, same age, older person, but all the dopaminergic neurons are intact. And in a Parkinsonian patient, the dopaminergic neurons go away, and that's when people become really, really sick. So we start here, we give the toxin, and the purpose of giving the toxin is to kill a certain number of dopaminergic neurons. And we wait 2 weeks before we intervene. Why? Because we want to simulate what happens in a patient. By the time a doctor sees a patient, about 70 to 80% of the dopaminergic neurons have died. What we want to do in this model is exactly the same thing. And then we want to ask those neurons that are remaining to become functional again. And this is a concept known as neurorestoration. And so we then measure function at 2 weeks after the drug and at 4 weeks after the drug. Now, if you look at this slide and you say, well, it appears that the dopaminergic neurons are all the same number in the model, in all the different groups. And it's supposed to be that way, because we cannot increase the number of dopaminergic neurons because many of them have died and we can't bring the neurons back to life. What we're attempting to do is to increase the function of the remaining dopaminergic neurons. That's the strategy. So these groups will come up again and again. That is the negative control. These are 3 doses of MAMF, and that is a positive control GDNF. And the number of dopaminergic neurons are the same in all 4. Now, the first result, obtained in collaboration with the neuroscience group at UCLA, is the most important, because it says when you do this, you give one dose of MAMF, and you look 2 weeks and 4 weeks later, and the only thing you need to know about this slide is that the lower the bar, the better it is, and the higher the bar, the worse the function. And you see that with 10 micrograms of MAMF, you have a very significant improvement in behavior, and with 36 micrograms, you have a significant improvement of behavior in 4 weeks. And this is the gold standard. There is no improvement in behavior. Now, I want to reiterate this again. This drug, although it does not improve the behavior, does support the survival of the neuron cell body, but it does not cause re-innovation of the striatum. And absent re-innovation of the striatum, there will be no functional recovery. Okay, that's got to keep that very clear. So these neurons are really quite special. They have an enormous arborization. As a matter of fact, one dopaminergic neuron supports 500,000 points of communication in the striatum. So they're really critically important. And what we're going to show you, you see 1, 2, 3, 4, we are going to cut through the whole volume of the striatum and show you that there is a re-innovation of the striatum in the presence of MAMF. So again, to reiterate, there's the cell body and there's the terminal field, the striatum. And we are attempting to stimulate the cell body so that it will re-innovate the striatum. So this is a field called densitometry. It's a computerized method. It can see things that the eyes can't see, and it was done in collaboration with Neuroscience Associates in Knoxville, Tennessee, and it was an extremely well executed program. So if you look at the shaded areas, 10 micrograms of MAMF, again, had a modest increase in density, and it was greater than that of GDNF on the far right. So we are not relying on one measure. We are looking at increase in behavior, and then we're looking at the density of the dopaminergic terminals in the striatum, and then we're going to be also looking at chemistry as well. So just a visual inspection of this field at the top 1, 2, 3, 4, those are the controls. The second layer, that's the negative control, 6-hydroxydopamine, and at the bottom is GDNF, which used to be the gold standard. And in between those, you see that there are varying degrees of re-innovation of the striatum. Now, the reason that 6-hydroxy and GDNF look so clear is not that you never see any terminals. In fact, the computer sees some terminals, but the human eye doesn't see them. But what's fascinating is that with all 3 doses of MAMF, you get varying degrees of re-innovation of the striatum. And this is what we want. This is the root cause of a lack of progress in the area. You can deliver drug after drug to the striatum. You will simply have to keep delivering the drug all the time. What you want to do is to restore the function of the dopaminergic neurons so that it reconnects with the striatum and in that way improve function. Now, these results were obtained last night, and this is the chemistry. And with full disclosure, the results look too good. And I questioned whether we should even show them in public. But they're preliminary results, which means that the experiment has to be done again. But what you see here is that 10 micrograms of MAMF had a huge effect in increasing the concentration of dopamine in the striatum. This project was done in collaboration with PharmaNet in Princeton, New Jersey, and it was done using gas chromatography mass spectrometry, which is a very, very precise and accurate technology. And my collaborator there happens to be a really good guy as well. And if you look at the axis, the y-axis, you would see that the n is 2 to 6. It's not a big n. But the results are internally consistent in that all of them are in the right direction. So the chemistry matches behavior, sort of spot on. And so for that reason, we thought it was legitimate to show this result, but we're going to have to repeat it. So, MAMF at the moment stands as a molecule that is unique, different from the other molecules in the space that it's competing with. On the basis of the data that we have at the moment, it reinnovates the striatum, which is the thing that we've been missing for the past 50 years. It's very difficult to believe this, but for the past 50 years, we've been trying to treat Parkinson's disease by giving the drug at the level of the striatum. And we have not been able to treat the root cause of the disease, which is improving or restoring the function of the dopaminergic neurons that remain. So, the philosophy of this company, of Amarantus, is that if you can catch those patients at diagnosis when they they still have about 20 to 30% of their dopaminergic neurons remaining. And the first order of the day is do no further harm. If you can then protect those neurons from dying, and further, if you can stimulate them so that they can produce a big reinnervation of the striatum, then we would be close to treating the underlying neuropathology of the disease. And that's not trivial, because at the moment, when you try to treat the disease at the level of the striatum, even as the symptoms of the patient improve, the dopaminergic neurons continue to die. And after about 7 to 8 years, they're all dead. And that's when you get chronic patients that are extremely difficult to treat. So MAMF reinnervates the striatum, it produces behavioral recovery, it increases dopamine concentration in the striatum, and there's something there which we haven't spoken about yet, improving protein folding. I haven't seen the hand go up yet for 1 minute, so it just did. So I just tell you very, very briefly that in 2008, to our great surprise, a guy called Glembotsky published a paper which said that MAMF not only can protect dopaminergic neurons, but it can also improve protein folding in the endoplasmic reticulum. And nobody expected this. And 2 years later, some people in Finland published some extraordinary papers explaining why that is so. And the bottom line is that MAMF is actually what we call a two-domain protein. One domain is responsible for acting on dopaminergic neurons, and the other domain is responsible for improving the function of the endoplasmic reticulum. So you like, in a sense, we can say, in using MAMF, you sort of have two shots on goal. One at the level of the phenotype of dopaminergic neurons, and at the other level of correcting the fundamental pathology at the level of the endoplasmic reticulum. And at the moment, there is no other molecule like this. The other molecule that is close to MAMF is something called CDNF, conserved dopaminergic neurotrophic factor. It's the competitive molecule. It has the dopaminergic actions of MAMF, but it doesn't have the endoplasmic reticulum actions of MAMF. And so because of that, MAMF is, quote-unquote, a superior molecule. So it's obvious from here what you do. You have to do primate studies, you have to do all of those things. And Bob Zimmerman is here, who is the guy in the company that is helping us along with those. And then you get your IND, and you do your phase 1, phase 2 clinical trial, and you take it from there. Thank you very much.
Ruben Field. Ruben Field.
So, we've been exposed to a lot of science here. I mean,
That guy is
hopefully you're
nuts.
not the sort of folk, you know, you can wake up now. One of the things we want to talk about is the commercial aspects of this. Dr. John has just, in a sense, explained the science and all the steps we have to do, and that's a long road. And we all realize that. Parkinson's disease is a tough disease. But because of all the breakthrough biology that's involved with MAM, which are listed there, and because of what he talked about, the C-terminal and N-terminal aspects of MAM, there are many other applications that we can look into, and which are being looked into at the moment. Cardiovascular disease, traumatic brain injury, stroke. And then we have identified and evaluated certain orphan diseases. See, one of the things is to become commercial, and that's my forte. And if you go back to the old days of biotech, the first biotech drug that came along was interferon, alpha interferon, but it didn't cure the common cold or the flu. It got approved for hairy cell leukemia, 500 patients a year. and then became a multi-billion-dollar product, hepatitis and other things. I mean, simply put, I mean, you have to have a strategy to get to the marketplace. So one of the aspects that I want to bring to the table is, besides the Parkinson's and the great science, I want to be able to get it to the marketplace. And take an example, Genzyme with Gaucher's disease became a tremendous product. Go back to my days at Amgen. EPO was only for kidney dialysis patients. Now it's used, you know, in all cancer patients. So we are looking definitely into these orphan diseases because we think with all this biology of man, and we already have identified some, and there are experiments going along, that we can certainly hasten MAMP to the marketplace, not just through PD. Thank you very much.
Thank you very much for the presentation. We will have our breakout in the Renaissance room.